multiply times that change is 0. If there is a vector that multiply times that matrix change is 0, then that vector satisfies this condition. That is, even though the structure has changed, that vector produces the same displacements in both at the measurements. Oops. There is then a theorem, which we prove being necessary and sufficient, but I will not go through the proof, but the point is this. If you found that vector, it can be proven that it will be exactly 0 stresses over the portion of the domain where there's been a change. It will be exactly 0 over here. Why? Because of minimum strain energy, because of this and that, but it's proof. Then, what happened? Escape. Okay, here is a simple illustration, right? They say picture is worth 1,000 words, so here is a picture. Academic example, but trying to keep at least some of the features in reality, meaning that the sensors are in Xeon, so we're not measuring everything, we're measuring some places, 1, 2, 3, for example. Because this is all academic, I'm saying only the spring that has the color has suffered a change. They were all 1, and now 1 has changed. The reason for choosing 0.5 is just to keep it a simple number, because this is all academic. I could have, as long as it's within the computational roundoff, it'll all be the same thing. Now, the flexibility matrix before the damage was computed from the data. Remember, we don't know the system, we just collect data. And it's this. Following 3 days, it's this. The change is this. In this case, it is simple enough that if you are willing to put a half hour or maybe 15 minutes, depending how clever, you might actually just figure it out without no theorem. You can just look at it and say it must be this. However, you can imagine that if it was a complex situation with sensors all over the place and you get this difference, it's not the simplest thing to say what happened. So the systematic approach follows as I'll try to illustrate. The singular value decomposition of this says basically that there is a null space of 2, meaning there are 2 sets of these loads. They happen to be on this basis. These are then treated as loads, and they keep, what am I trying to do? Yeah, the first load is in cyan, the second is in this green. At this point, we have to have a model. The computation of the loads is model independent, but the computation of the stress field that says where the damage is, of course, requires a model of the original system. The stress field is computed, and as you can see, it is 0 over the only part of the domain where there's been a change. In other words, it's bypassed. It's gone around. For that load, the change in this spring is entirely unobservable. Okay, so we would say their damage is on the spring with the zeros. Well, at the end of this point, we decided that we needed to do something beyond statics, that was flexibility, in order to address the problem that Danny has with the part. So we take this thing to the dynamic domain, and it gets, there's some Laplace transforms and some things, but here's an illustration. Here is a system of 3 levels, building-looking thing, with the damage on the second level. The idea is that you can go through some sort of mathematics that tells you, out of infinite possibilities, this is a realization of dynamic excitations here and here, obtained without knowing what the system is, that will bypass whatever change there was. When you calculate the resultant stresses, you can see that level 2 is stationary at 0. This is something due to an initial condition issue. But anyway, you can see, with flexibility, it would be entirely impossible to distinguish between these 2 points. Okay. It turns out that the next, well, maybe I can skip this, because this just means that if anybody's going to pay any attention, they're not going to be doing dynamic analysis for dynamic loads to see stress fields. So we were trying to come up with something practical. It turns out that in the Laplace domain, you can keep it all algebra. And the one interesting thing that most structural engineers like, at least find amusing, is that what happens in the dynamic case is you can take the problem to be the calculation of a stress field that is complex. So you actually load the structure with 3 plus 4i loads and 5 plus 9i and so on, and get a complex stress field that in this case, as you can see, bypasses, here is shown with magnitude and phase, bypasses the damage. there is really nothing to it once you think about it a little bit, but it's kind of amusing to find loads with imaginary parts. This is an application on a plate. Again, this plate was taken from the literature. The point that I was trying to make with this plate, when I put this on a paper, was that this technique may or may not be able to solve the problem you have, because we might not be able to get the feature with sufficient accuracy and so on. But if the problem is defined in the way that it was defined in this paper, that is, here is a plate, I'm going to reduce the modulus of elasticity of element 29 by 5%. Can you tell me which element decreased? By measuring along this line 9 sensors. Because it's theory, I can look and say, yes, I can, and I can do it exactly. It doesn't really matter because the conditions are satisfied. So here you can see that the metric that is computed is, of course, exactly 0 at element 29. It's obtained from the data. So the summary then, well, no, 2 more slides, I think, on this. One is that there is saturation. As I said at the beginning, do these loads exist? When Danny approached me, can you help us find the damage? I said, with the null space approach, I said, well, I don't know. Probably not, because it's probably going to saturate. Saturate is something that means these loads won't exist. Well, can you come up with something? So we've been trying to develop this idea that might give information when there is saturation. And in the name of time, I'm going to go to how it works at the end. This is a plate with 3 cracks. The number of sensors is small, so that when you do the theory, it tells you there is no hole. You cannot find loads that will bypass the 3 cracks simultaneously. The plate is now replaced by this finite element mesh. So no longer am I talking about the real plate, I'm talking about this finite element mesh, which happens to have 356 nodes. We assume that we were able to identify the bandwidth from data from here to here, so that fraction to scale. What happens then is, this is too detailed, but the theory says there is no way that you can apply the theory and say it's here. What you can do, apparently, is to rank the elements in order of most likely, meaning stress being low. You cannot get zeros anymore. I don't know that there were 3 cracks. There could have been 1, 5, whatever. So after applying all this technique, the elements in the finite element mesh have been ranked. And this is the one that was more likely. So nicely, it was with one of them. This is second most likely. This was third most likely. So that was great. But of course, we don't know that there were 3 cracks. So the question is, what is the 4th more likely, and the 5th, and the 6th, and the 7th, and the 8th, and the 9th, and the 10th? Okay, so by this time, you might say, okay, it seems that there is some indication that maybe something is going on within these regions. So we will look there in the next stage. So this is the final perspective to conclude on this general sort of idea. What is a necessary condition? For the theory to apply exactly, these loads must exist, otherwise it's impossible to find them. And the conditions for existence are well defined. They're not always satisfied. And yeah, this I think this is the last slide before, yeah, one before last. What happens in the end is this. This matrix that we calculate from the data, it's really this guy, but in reality, due to